All right, here's a question for you. What comes before addition? I know, it sounds kind of like a trick question, right? But today, we're going to dive into a mathematical operation that actually sits underneath it all. It's called zeration, and trust me, by the end of this, it's going to challenge a rule about numbers you've probably taken for granted your entire life.
So, to get our heads around this, let's start with a question that seems, well, almost silly. Is a times 2 times always the same as 2 times a? I mean, in every single math class you've ever been in, the answer was a big, fat yes. It's just a basic rule of the universe, right?
Well, what if I told you there's a strange new kind of number out there where the answer is no? A number where the order you multiply in completely changes the final result. Yeah, that's the rabbit hole we're jumping down today.
Okay, so to understand how this is even possible, we need to zoom out a bit and look at arithmetic in a totally new way. I want you to picture it like a ladder. Every single rung on this ladder is built by just repeating the operation from the rung right below it.
Way up at the top, at what we'll call rank 4, we've got this wild operation called tetration. And what is that? It's just repeated exponentiation. You know, when you see those crazy towers of powers, that's tetration.
Okay, let's step down one rung to rank 3. Here, things get a lot more familiar. We're talking about exponentiation. And that's really just a fancy way of saying repeated multiplication, right? 2 to the power of 3 is just 2 times 2 times 2.
And what about multiplication down at rank 2? Well, that's just repeated addition. 2 times 3 is really just 2 plus 2 plus 2. You're starting to see the pattern here, right? Each step up the ladder is just a shortcut for doing the step below it over and over again.
And that brings us all the way down to rank 1, good old addition. This is the bedrock, the foundation of pretty much all the math we do every single day. And it really feels like the bottom of the ladder. But is it?
And that is the million-dollar question. If this pattern holds, there has to be something below addition, a rank 0, an operation that's so fundamental, it's like the foundation beneath the foundation. So what in the world could possibly come before addition?
Well, the answer is an operation called zerating. And its core rule is actually super simple. When you zerate two different numbers, the result is just one more than whichever number was bigger. Let's just do a quick example. Say you have 3 zero-rated by 5. Okay? Which one's bigger? 5. So you just take 5, add 1, and your answer is 6. That's literally all there is to it. It's basically an operation for finding the next number up from the bigger of the two you started with.
Okay, so this is where it all starts to get really fascinating. If you look at the history of math, there's this incredible pattern. Every time we humans define a new operation, the act of trying to undo it, to find its inverse, forces us to invent completely new kinds of numbers we never even knew we needed.
And this just lays it out perfectly. We couldn't solve something like 5 minus 7, so boom, we invented negative numbers. We couldn't do 7 divided by 2, so we came up with rational numbers, fractions. We needed to find the square root of -1, so we had to invent imaginary numbers. So what do you think happens when we try to undo zerization? You guessed it, we're forced to invent something brand new, delta numbers.
So this new inverse operation, we're going to call it deltation. It just flips the whole thing around. If A zerated with B gives you C, then C deltated with B gets you right back to A. Sounds simple enough, doesn't it? But trust me, when you follow this logic all the way through, you end up in some very, very strange territory.
And to see just how strange it gets, we actually need to connect it to a really old mathematical fight, one that stumped absolute giants of the field, like Euler. And the whole thing centers on a question that seems impossible to answer. What is the logarithm of a negative number?
Okay, so here's the paradox that drove people nuts. If you take the natural log of -1 squared, well, -1 squared is just 1, and the natural log of 1 is 0. Easy. But hold on. A basic rule of logarithms says you can just pull that exponent of 2 out to the front, so it should also equal 2 times the log of -1. If both sides are equal, that means the log of -1 has to be 0. But it can't be. We just said only the log of 1 is 0. This contradiction was a huge puzzle for centuries.
And here it is. This is the big moment. It turns out that these weird new delta numbers, the ones born from undoing zeration, they give us a completely new way to handle the logarithms of negative numbers. They actually solve this ancient paradox.
So here's the official connection. We can basically define a delta number, let's say delta x, as being the same thing as the natural log of -x.
And this one little bridge connecting two ideas that seemed totally unrelated, that's what gives delta numbers all of their weird and powerful properties.
And believe me, those properties are bizarre. The second you let delta numbers into your equations, all the comfortable, cozy rules of arithmetic, they start to bend and even shatter. Suddenly, the order you multiply things in, something we have always taken for granted, becomes absolutely critical.
All right, check this out. These are the new rules for multiplication, and you have to look close because they are not symmetrical. See, if you take a delta number and multiply it by an integer, doesn't matter if it's even or odd, the integer gets sucked inside the delta. But if you take a regular number and multiply it by a delta number, it stays on the outside. The order you write them in gives you a totally different result. This right here, this is the whole thing. This is the clue that cracks the entire case. And boom, that brings us right back to the question we started with. Because of those lopsided rules, multiplying a delta number times 2 is not the same as multiplying 2 times a delta number. The commutative law of multiplication, a rule that's been a cornerstone of math forever, is broken.
Now I know what you might be thinking. Okay, that's a cool party trick, but so what? Why go through all this trouble to invent a system just to break a rule? And that is a totally fair question. Is this all just a fun little game for mathematicians with too much time on their hands?
The answer is a hard no, because these ideas actually have some seriously powerful applications. Take, for example, trying to define a perfect on-off switch in math, what's called a step function. The old way of doing it involves these ridiculously complicated and messy formulas with limits and error functions. Just look at this thing. It's a clunky mess.
But when you use the language of zeration, that exact same perfect on-off switch can be written with this stunningly simple and elegant little formula. No limits, no special functions, none of that mess. It just works. This is the real power behind all of this. Finding the right ideas can turn something that looks impossibly complex into something that's beautifully simple.
And that really leads us to the big takeaway here. For centuries, the basic rules of arithmetic seemed, absolute, carved in stone. But today, we watched one of them just fall apart. It really makes you wonder, doesn't it? What other unbreakable laws of math are just sitting there, not quite as solid as we think, just waiting for someone to ask the right question and invent a new number to break them? Hey, thanks so much for joining me on this deep dive into zerization. It was a lot of fun. Until next time, keep questioning everything.